Welcome back, everyone, to Complex Analysis. So today we're going to close out the chapter with a discussion on constant functions. And then we're going to talk about a result that can somewhat be extended from calculus to complex analysis, although we're going to have to be really tricky about it, and we'll see that in a second. In the meantime, remember, what is a constant function? A constant function is a function whose output is always the same thing. So for instance, f of z equal to 1, or f of z equal to 0, or f of z equal to I, or maybe f of z equal to 3 minus I. In any case, it's a function that no matter what you plug into it, you always get the same value out. So it's constant. Its output's always constant. Okay, so these are the functions that we're going to be discussing in a way in today's video. So recall back from calculus, we have what's called the mean value theorem. And the mean value theorem says the following. So suppose that f is continuous on the closed interval ab, and it's differentiable on the open interval ab. Okay? So if you have a function that satisfies these two things, then you know that there exists some c, although we don't know what that c is, but there's some c in the open interval ab such that f prime of c is equal to f of b minus f of a all over b minus a. Okay? So remember, this is kind of like what's happening in the picture. So let's say we have our function. Here's a, here's b, and maybe we have something like, I don't know, something like that. Okay? So what this formula is saying is that there exists some c such that if you plug it into the derivative, you get essentially this slope value here. So if you look at the right-hand side, f of b minus f of a over b minus a, if you remember from the really, really beginning parts of differential calculus, this is really just the slope of the secant line through f of a and f of b. So in our picture here, here's f of a, whoops, here's f of b. So the secant line that joins these two, let's pretend like that's a straight line, would be this line right here. Okay, so the right-hand side of this equation is just the slope of this line. Okay. Now what the mean value theorem is saying is that there's some point in this interval, which from our graph it looks like it's probably going to be about right here, c. Oops, let's use a different color that you can actually see. Let's use purple. There we go. So there's some point in this interval AB, and we're going to call it C, where the derivative, remember the derivative is just the slope of the tangent line. So you're going to get some point where the slope of the tangent line is actually equal to the slope of the secant line right here. So notice these two lines have the same slope. And that's what the mean value theorem is saying. Now mean, what do we mean by mean? We don't mean by like it's a mean theorem, like it's angry or is not nice or anything. What we mean is average, right? Slope you can think about as average. So that's why we call it it's almost like the average value theorem in a way. We're saying that the derivative achieves this average, f of b minus f of a over b minus a. Okay, now from the mean value theorem you get a lot of cool things. First of all, you get Rolle's theorem. Whoops. Which says that, well, if you have a function who's continuous on AB, differentiable on AB, and if you know that f of b equals f of a, then you know that there's some point c where the derivative vanishes or the derivative is 0. Okay, so that's Rolle's theorem. And if you remember back from calculus, well, maybe you've seen this exercise or not, usually that's really useful in determining roots of a polynomial or how many roots a polynomial has. One little really cool application, although I'm kind of biased because I like algebra, but in any case, another result that we have is the following. Okay, so let I be an interval, and suppose that f is a function from I to r such that its derivative is 0 for all x in I. Okay, so if you have a function from an interval to the real numbers, so our inputs are real, our outputs are real, and the derivative of this function is always 0, then this result says that your function is a constant function. Now, why is that true? Well, let's give a little proof of this. Proof. Okay, so let a and b, this interval, be contained in I. Okay, so I is some kind of open interval. We can always find a closed interval a, b that lives in there. Okay, so by the mean value theorem, okay, we have that f prime of c is equal to f of b minus f of a over b minus a. Okay, well, what do we know about the derivative, though? F prime of c, by our assumption in this theorem, is always 0. So we really have 0 is equal to f of b minus f of a all over b minus a. Multiply both sides by b minus a. And we get that 0 is equal to f of b minus f of a, or in other words, f of b equals f of a. Whoops. I mean, that's definitely a true equation or a true statement there, that f of b equals f of b, but I meant to say f of b equals f of a. Okay? And what that means for us is that, notice a and b, they were arbitrary, right? So what this is telling us in this proof is that f only has the same output. It's whatever this is. And what does that mean? That means that f had to be a constant function. So therefore, f is constant. I don't know what the constant is, but I do know that it is constant, though. Okay? So that's a result that we have back in calculus. So if your function, if your real valued function has a derivative of 0 at every x in your interval, okay, then your function had to be constant. Which sort of makes sense, right? If your derivative is, what's one of our derivative rules? It's the derivative of a constant is 0. So what this theorem is kind of saying, well, if you have a function whose derivative is 0 everywhere, then your function had to be a constant to begin with. So it kind of goes in line with our intuition in a way. Okay, but what about complex analysis? We're not dealing with we're not doing calculus, right? We're doing complex analysis. So in order to get this result in complex analysis, what we have to do is we have to talk about the mean value theorem of complex analysis. Okay. Now, what does the mean value theorem of complex analysis say? The mean value theorem says,
Jeff, there is no mean value theorem of complex analysis.
Unfortunately, there actually is no mean value theorem in complex analysis. Later on, we may see, if we get far enough, there's something called the mean value principle of complex analysis, but we don't really have a complex analog for the mean value theorem, unfortunately. So we're going to have to prove this result, this constant result, in a different way. And what I mean by constant result, I mean, well, if you have a complex function whose derivative is always 0, then this implies that that function had to be a constant to begin with. So we have some work to do. We have to do a little bit different. Okay. So to prove this, we're going to have to assume a couple of things. So first of all, we're going to have to assume that our function is differentiable everywhere in its domain, which sort of makes sense if you think about this result anyway, because we're assuming the derivative is 0, so that means that the derivative has to exist, right? Okay, so that one shouldn't be too crazy. Now, the second assumption might seem a little weird, but this actually goes into how we're going to prove this, or this hypothesis here is allowing us to prove our result. So we're going to also assume that our domain is connected. And by connected, I want you to think of it's just some kind of blob that you can connect every point with a line in some way. Okay, this is kind of going back to chapter 1 a little bit, but in any case, kind of think about that. It's some blob that's connected. It has one whole piece, and we can sort of connect everything with lines. Okay. Now I'm thinking about pi. Fantastic. Okay, so here's our complex result. So let G be a region, and remember, a region in complex analysis, region just means open and connected. So I'm going to give you a picture. Suppose G kind of looks like maybe something like this. Some weird blob. And I'm doing the dotted lines because we're dealing with an open set here. But it's an open connected set. Okay. Now suppose we have some complex valued function f from G to C. Okay. And by the way, G is a subset of C here, so it's some blob in the real or in the complex plane. And we have some complex valued function f. Okay. Now let's suppose that f prime of z is defined and equal to 0 for all z in your domain here. So just like we had in the complex result, we're supposing that our derivative is 0 everywhere. Then the result that we want to prove is that, just like it was in calculus, f had to be a constant function. Now, like I said earlier, we don't have a mean value theorem for complex analysis, so this is going to be a little bit more difficult, and it's actually kind of cool, but it's a little bit more work, though, to actually get this. Okay, so how do we prove this? So proof. So we're going to approach this in a very, very, very slick way. This is, again, one of those cases where some mathematician had to pull this out of thin air, and then it worked amazingly. So what we're going to do is we're going to prove that f is constant, okay, meaning it has the same output. F is constant on every horizontal line and vertical line in G. Okay, so if this is our G here in the upper right hand corner, so what we're going to be proving is that our function is constant on every horizontal line in G. Okay, so let's imagine these are our horizontal lines, and every vertical line in G as well. And you might be notice that they're crossing, right? That's totally intentional. We do need these to intersect as well for the following reason. So if we can show this, if we can show that it's constant on all of our horizontal green lines here and all of our vertical blue lines here, what this essentially is saying is that, well, let's say that the value on this green line right here, let's say that the output is C. Okay, well, since this green line intersects all of these blue lines here, 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 and here, then that means that the output on all these vertical lines, I'm going to color them in green on purpose here, are all C as well. Okay, but on the other hand, all these vertical lines are crossing all the other horizontal lines, right? So then we get that the output is C there as too. So it's this really, really cool chain reaction that's going to go on. If we prove that it's true for all the horizontal and vertical lines, because all the vertical lines and horizontal lines intersect, we're actually going to get the same output for every single horizontal line and vertical line. I'm going to put here, it's a chain reaction. Okay. Now that seems like it might be super, super hard. Remember, we're going to do this in general, so it's not like we're proving it for every single line or horizontal and vertical line, because it's probably impossible to do by hand, because there's probably infinitely many of them. But we're going to be able to do it nonetheless. All right. So how do we actually do this, though? Enough talk. Now math. All right. I'm going to do this in purple. So let's go ahead and we're going to do horizontal lines first. So let H be some horizontal line in G. Okay, so maybe this is our horizontal line right here. Okay. All right. So if this is a horizontal line, okay, and this is, by the way, G in our domain, okay, if this is a horizontal line, what that means is that for every Z and H, okay, since it's on a horizontal line, that means that all points have to have the same imaginary component. So for every Z and H, we know that the imaginary part of Z is always the same thing. And let's call that same thing Y naught. Because why not? Okay. So we have a horizontal line, which we're calling H here, that's in G. And since we're dealing with a horizontal line, just think about the complex plane. That means that your imaginary part, okay, has to be the same thing for all points on that horizontal line. Okay. Now, why do we like this, or what's the point of this? So now let's go ahead and let f of z, okay, like we did in the previous video, we're going to write f of z in terms of its real and imaginary parts. So write f of z as u of z plus I times v of z. Okay, remember that's the real and the imaginary part there. Okay. Now, since the imaginary part of z is always equal to y naught, okay, we can think about the real part, u of z, which we can also think about as u of x comma y. This is really just u of x comma y naught. Since the y naught there is always constant, the second coordinate is basically always constant as well. And so we can think about this as a single variable function in x. Single variable function of x. Okay. Let me give you an example really quick, just to kind of bring that home. So for instance, a small example, let's suppose that u of xy, was equal to 2x minus 3y plus 4. Okay, so if we know that this y is a constant number, maybe, for example, let's say y is 4, then our function u of x4 will become 2x minus 3 times 4 plus 4, which is equal to 2x, minus 8. Okay, and so notice what do we have over here? We have now a single variable function u of x. Okay, so knowing that your second coordinate here is constant, that actually turns your function into a nice single variable function. Okay, what's the point of this though? All right, so now what this enables us to do, this actually enables us to sort of bring it back down to calculus in a way. So what do we know? We know, well, f of z is equal to u sub x plus I'm sorry, not u sub x, u of x plus, I mean, that's fine. We'll say u of x right now, plus I v of x comma y. Okay. That's what we know at this point, because again, remember our u now is a single variable function in x. Okay. All right, so now that we know that, we also know that f prime of z is equal to 0. Remember, that's our initial assumption, right, that the derivative is 0 in all places. Well, what is u sub x? So the partial of u with respect to x, this is actually equal to just the real part of f prime of z. So think about taking the derivative of this whole thing with respect to x. Then the real part is just going to be the partial of u with respect to x. So that's what this equation here is saying. Okay. Now, what do we know about the derivative of f? We know that that's 0. So this is just the real part of 0. And what is the real part of 0? That's just the number 0. So what we're showing here is that the derivative of u, okay, which since it's a single variable function, that's just u prime of x, is always 0. And u is a real valued function. Real valued function. Okay, so what did we just talk about in single variable calculus? Well, what happens when you have a real valued function, single variable, whose derivative is always 0? What do we know? This implies that u has to be constant. We'll call it a naught. Okay. So again, this idea that since we fixed our y-coordinate to be something, that turned our u into a single variable function, and then using our assumption about f prime of z, that told us that this single variable function actually had a derivative of 0 as well, and so our results from calculus actually tell us that u is a constant. Okay, so a similar argument, okay, shows that v is also constant. Okay, so you kind of just replace the u's with the v's, or you replace that argument, whoops. Instead of focusing on u as being a single variable function, you can actually also say that v is a single variable function, and then using calculus again, you can show that that is constant. So therefore, f of z, which is equal to u plus iv, is actually equal to a naught plus I, and let's call this constant for v, let's call it b naught, because why not? B naught. Hence, f of z is constant, okay, that's a constant number right there. These are all constants now. Is constant on h, our horizontal line. Now, h was arbitrary, right? We picked any horizontal line. We didn't actually pick on a particular one. So this is actually true. Therefore, f of z is constant on all horizontal lines. Because again, remember, our h here was arbitrary. We picked any horizontal line. Okay. Now note, to prove that f is constant on all vertical lines is virtually identical to what we just did, except instead of playing on the imaginary part, you're playing on the real part. Okay, so for vertical lines, so I'll denote with capital V, you can prove f is constant, okay, by a similar argument okay, with imaginary part of z being replaced with the real part. By real part of z. Now the reason for this is, well, if you have a vertical line, let's say again this is g, right? If you have a vertical line in g here, okay, what does that mean about every single point on this vertical line? That means the real part has to be the same thing. Okay, so that's why you can sort of play the same exact game that we just did, but now with the real part. Okay, so therefore, f of z is constant on all horizontal / vertical lines. And therefore, by that chain, that what did I call it earlier? That chain reaction, and is therefore, so pinkies up everyone, therefore constant on all of g as desired. Boom. All right, and that's the proof. So we have that if you have a complex valued function whose derivative is 0, then you know that that function's a constant, just like we had back in calculus. All right, so that's the end for chapter 2. In chapter 3, we are going to get into different types of functions. So I will see you all then.